I want to talk about restricted Boltzmann machine. And it reminds me the Ising model in physics because it's all about energy and is inspired by physics. It's a very important article in 2006. So this is the beginning of deep learning, but is rarely used now. So we have some inputs and some bias such as CK, and these are inputs. So X, it's visible, sometimes we call it V. And then we have some weight, and then we have some outputs, which we call it hidden layers or edge. But these are binary units. And here we have some BJ, which is BJ and CK are biases. The things that I like semantic hashing and these interesting binary things, binary coding. So semantic hashing is about your representation is in binary. The thing that I like is because you can connect the world of computer science, which is for example is about combinatorial optimization and graphs and those things which we used to use. You have to use STP relaxations and linear programming and those things. So you need to round it and come back to the original discrete units. So this is a way that we can connect discrete mathematics to continuous mathematics very systematically and in an explainable fashion, as is declared in. So maybe the future of explainable AI is all about using these tools. So they're very important for me. And the energy E of input and hidden variable, hidden layer is the energy is minus H transpose WX. And so W is your parameter that you have to estimate. So minus C transpose X minus B transpose H. So B and C and W are your parameters. So you can write it as minus J K W J K at J X K minus C K X K minus B J at J. Summation over K, summation over J. So the distribution is P of X and H is just exponential. E to the minus energy divided by a partition function. This is a partition function which is intractable like many other problems. So this paradigm has been used in several different contexts, in Gaussian processes, here in machine learning, in many problems in machine learning. And you can easily prove that P of H given X is just the product of P of Hj's, which are Bernoulli, given X. So P of, for example, if J is 1 given X, you can see that in this model, in this Boltzmann machine, it's 1 to the Bj plus Wjx. And this is the sigmoid of Bj plus Wjx, which is this is just the jth row of W. The same thing for X, P of X given H, you can approximate it by P of Xk given H over all K, and for example P of X equal to 1 given H is explicitly this distribution CK plus H transpose W When we say minus k, it means k's columns of W. And this is the sigmoid of ck plus h transpose wk. And so P of x and h is intractable, but because P of h given P of h given x is easy to compute. Why? Because you can write it as P of h and x divided by P and x. And we want to maximize the likelihood. So the log likelihood is just L of W, B, and C. All of them, as before, we usually write them as theta. And then this is the summation over T, log of P of X T. So this becomes T from 1 to n log of P of X, T, and H. And you can simplify this to T from 1 to n log of minus energy of xt and h, and minus n log of z. And as I said before, z is just summation over this, e to the minus energy of x and h. And if you just take the derivative with respect to theta, so w theta of L of t, theta is of interest, so we can calculate it using just simple mathematics, log of e to the minus e of xt and h minus n gradient of log of x and h e to the minus energy. And that's easy because you can write it as expectation derived from probability of h given xt of so we are just simplifying it, and minus n expectation of now P of h and x, gradient of theta minus energy of x and h. So this is all about Boltzmann machines. So now we want to think word that that co-occurs with an example. For example, cow, drink, babies, calcium, and then it reminds you it's all about milk. So meaning of a word is determined by the word that it co-occurs with. So the meaning is just the probability that the word and when C co-occurs in window of, for example, some size. Usually we use window size of 5 in the corpus. But a better measure is point-wise mutual information. Well, I've used mutual information in several articles, and I really enjoy the concept of mutual information and information theory. Because again, it's another way to find ambiguity. So point-wise mutual information, so we can write NW of C is the log of P of W and C, P of W, P of C. So it's like correlation of a word in a context. And you know that Mikolov et al. Have explained that it has simple functional form to predict word. For example, from 5 surrounding words. So the probability that W given W1, W5 is just proportional to VW dot 1/5 of aggregation. I mean summation, a simple summation. And then now I want to talk about semantic spaces, semantic hashing, and those important things. And maybe transfer learning, maybe federated multitask learning, and those things, how use those things in the context of natural language processing. So in semantic space, you know, each word is associated with a vector. In cognitive science, they usually talk about the same thing. So this is a latent variable. We don't know it and we want to capture it using several techniques in word representations. But think like this, that your corpus is generated by a random walk. So the corpus could be generated by a random walk of a, for example, discourse vector C on the unit sphere in RD. So it goes like this. It's just a random walk. From one word it goes to another word, and suddenly you notice that you have generated a book, a good text, a poem. So the probability that W is output given C of T is proportional to VW.C of T. And I'm sure that you have seen my lectures about those linear LDA method, those word embedding, skipgram, and of course I didn't talk about GLOVE, which is really important. And so the assumption is, so instead of this, let's talk about a very important article in 2016 about word embedding. Word embedding. The title is Word Embedding as Metric Recovery in Semantic Spaces. It was a very nice article. And the GLOVE, it's an alternative to the skipgram that I told you about word representation. It's much easier, and as the name suggests, it's just a global vector for word representation. So let's compare these things. So we have word-to-vec algorithm, such as skipgram. For example, you combine it with negative sampling. And then you have another paradigm, which is GLOVE. But the thing about GLOVE, you can run it in parallel. You can do it over multiple CPU. It is good when your CPU is very large. So it is based on count-based model, while word-to-vec is just a predictive model. For example, at each time you take a window around your center word, and you move the center word, and you keep track of all of your words in your text. But in count-based model, you just learn vectors by doing dimensionality reduction in the co-occurrences count matrix. So the motivation for, of course, the word to vec, if you remember, the probability of output given context is just e to the u transpose vc divided by the sum over u transpose vc. But you may ask yourself, why not you capture co-occurrence counts directly? Well, that is in Glow, we have two options really. You can either use the window, use window around each word, very similar to idea of scriptgram, but of course it's global, you're just counting. And the other option that you could use is just using Word document. It means that co-occurrence matrix will give general topics leading to latent semantic analysis. Let me give you an example. For example, I say, I like computer science, I like algorithm, I teach probability theory. For example, the number, if you count, I like, in the text that is just 3 sentences that I told you, if you count just the, with window of 1, of course, very simple things. So if you count this, you notice that I've used like 2 times, because I said I like computer science, I like algorithm. So like is used 2 times, and of course here it is very symmetric. In computer 0 time, and science 0 time. For example, and if you complete this, you will notice that you have a super simple representation. For example, like is just 2010. So it's a super simple, very fast representation of a word. But anything that is too good to be true has some problems. For example, it increases in size with vocabulary. It is very high dimensional, and the models are less robust. But the GLOVy is a trade-off. It means that you have a cost function, for example, u and v are your parameters, and then so your cost function is f of pij ui transpose vj minus log of pij squared. So you log the count of pairs, because this is a scalar. And this is a scalar because, and you do it for all, because you do it all pairs of words. And F is just a weight matrix, and you don't like the words like the, because you use it very much. It happens a lot. So your F function is like this. Some words you want to teach the machine that these words are used very frequently. So don't be fooled and take those things into considerations. So that's what F represents, and Pij, as I said, is just a co-occurrence matrix. And your final representation is just U plus V. Because for any word, you have either word representation and the context representation. So so we aggregate them in a simple way. So we add them together. Now I want to talk about the article that I promised about word embedding as metric recovery in semantic spaces. It is written by Tatsunori Hashimoto. and it is used in cognitive psychometric literature because semantic spaces are just vector spaces over concepts. And